Okay, I think I'm actually 1 minute late, so we can begin. Hi everyone, welcome back to COP 3402. Today I want to begin by going over the homework. So I think this was the homework from last time, correct? Homework 3 and then homework 4 as well. Okay, so I guess we can start. I'll ask you all the first question. What happens if I already pushed my repo to the grading server, but then I create a new repo from scratch and try to push it? Yeah.
You'll get an error because the histories won't match.
Yes, exactly. There'll be a conflicting history. Yeah. How can I resolve that error? Does anyone know? Remember from last time?
So you should move what you have to like a backup folder, and then use git clone, and then add any to get the remote repository, and then add any changes in the backup folder that you want to push.
So that might work. There's another approach that's more typical, I would say, for solving a problem. Yeah.
Are you supposed to pull the remote one to your local and then resolve the conflicts?
Yes, yes. You would run git pull the changes to your remote that are not in your local repository, and then resolve those changes like you saw me do somewhat painfully last time. So, yeah. And how do I get my repo if I've already deleted my local repo? So my repo does not exist. What command can I use to get my repo if it doesn't exist locally? Git clone, exactly. So you'd use git pull if the repo already existed and you were inside of the local copy, you would pull those changes. But if it didn't already exist, you'd have to run git clone to create a fresh copy of the remote. Okay, so now for the second question. First row, if you're using a text editor, Vim or Emacs here in this case, what part of the Git repository will be modified?
Working directory?
Yeah, the working directory, because you're making changes presumably to files that have not been, well, the changes you make are not going to be automatically added or committed. They'll be untracked, yeah, as of yet, so, yeah. And then git add, what would that modify? The staging area, so when you run git add, you move changes to the staging area. And then git commit, the local, because you're committing those changes to your local repositories database. Where is that database? Your machine, but where specifically? When you run git init, what is created for storing these changes?
Index?
There is an index of changes, but what is it called? What is that? What is the specific file called that is created? Not patch. When I run git init, I'll show you as a demo here then. Yeah, if I run git init on my desktop, it says initialize empty git repository and home bpappets desktop.git. So when you run git init, it creates a .git directory for storing all those local changes. I'm going to delete all of this. So git pull, what does that make changes to?
The working directory.
Not the working directory, but someone else said it. Yeah, the local repository. So you're pulling the changes, so the changes will not be in the working directory because they've already been committed to the remote. You're adding them to your local's commit history. So they're going to bypass the other stages and go immediately to the local repository's commit history. Not so much bypassing as just going directly to the commit history. And then conversely, git push, what does that modify? The remote, correct? Because you're copying changes from, or commits from your local repo to the remote in that case. Okay, let's go to question or homework 4. Do make files use tab characters or space characters for indentation? Tabs, yeah. Consider the following rule. What is the target? Hello. What is the prereq? Let's see, and then the recipe.
GCC, echo.
Yeah. Process of elimination. It's the last thing here. So.
Yeah.
In the above rule, what happens if you run make twice in a row, assuming the hello.c build successfully, the hello binary build successfully the first time?
It'll check the timestamp, and when it sees there's nothing new, it won't do anything.
Yeah, exactly. Nothing will happen. How could we tell make to run the hello command every single time, regardless of whether a hello file exists? What did we do last time when we had that clean rule?
We would add hello as a prerequisite to .phony.
Yes, exactly. We would add it as a phony prereq. That's a special target in make, that if you add a file as a prereq to phony, .phony, it would always run that command. Has anyone read The Catcher in the Rye? Random question. The character in that book mentions phonies a lot, so I thought it was relevant, but okay. That brings us to,
Can you briefly explain the dot phony again?
Yeah. So I can actually, I can show it. If I have a make rule to create a file, I'll just call this test.txt, and we'll say that test.txt is created by saying touch test.txt. So the command touch just creates a file. I can run it here. And then if I run ls, you can see there's a file called test.txt. It's an empty file. Touch just creates an empty file by default. If I were to run make now, it would create that file. If I run it again, it says test.txt is up to date. What I'll do is split my window here. Oops. I could say .phony and add test.txt to the .phony rule, or as a prereq for .phony. And now if I run make, every time it's going to run the recipe to create test.txt.
Ignore the timestamps.
It just, it tells make that the target is not, really it's not a target that you want to check for timestamps, yeah. Just run it regardless. Typically you wouldn't use this for a file. This example is kind of contrived. You use it for a command like clean, where you'd want to always run the clean command every time, regardless of whether there's a file named clean that already exists. So now if I can run that, and then if I touch a file called clean, it keeps running even though there's a file called clean in my current directory. That's the idea when you want to use .phony. Okay. So, any other questions before we start with today's lecture on file systems? All right, so today we're going to be looking at basics of file systems. Some of this will be review from the first lecture on paths, absolute paths, relative paths. I think a lot of this material will be somewhat intuitively maybe obvious or familiar with a lot of you since you've used computers before, but there are some nuance here that is easy, I think, to miss. So you should still probably pay close attention to what's going on today. And this lecture should be a bit slower or less dense than other lectures because it was originally one lecture when I taught the course last semester, so I'm not compressing it with 2 other lectures today. We only have this lecture and that's it. So it should be a bit, I guess, more manageable to digest. Okay, so like I said, many of you probably used a file browser before. I guess by a show of hands, who used Windows in here? And who uses Mac OS? And who uses Linux? Okay, more than I thought. I think it's growing every year, the number of Linux users. You probably interact with files through a file browser. Does anyone not use a file browser here?
Depends on the project, but yeah.
Okay, yeah. So if you've only used a file browser to interact with files, you might think that a file's path, the file you see as this icon here, is the same thing as the file. But as we're going to review throughout this lecture, that's not really the case. It's more like this file path is like a map, and the byte sequence, the bits that a file actually is associated with, is like the territory. So this is a classic problem, map versus the territory. So what I'm trying to say here is that a file is an abstraction. So what is an abstraction? Does anyone know what an abstraction is? Can anyone tell me what an abstraction is or define it?
Abstractions are basically a way to hide away complexity in like a simple interface.
Yeah, exactly. So with an abstraction, to abstract something, you take a specific solution to a specific problem, and you abstract away, kind of hide some of these specifics to make the solution more general for other use cases. Now, the problem is that by hiding some of the details, you make solutions sometimes more complex. But abstractions are very useful. There's many kinds of examples of abstractions beyond that of in the realm of computer science. So for lock and key, we have different kinds of locks that exist. So we have tumbler locks, wafer locks. Those are physical locks that exist. These are both implementations of a lock and key mechanism. Now, digitally, we also have other ways of implementing locks. So you have like a login password. The login screen on Eustace is like the lock, and your password is the key for that lock. And then we have cryptographic keys as well. You can use these as well to log into Eustace more swiftly. Another physical abstraction would be a steering wheel. So back in the old days, they had rack and pinion steering wheels, which let you control a steering wheel totally physically without using any sort of automated electrical assistance, and then drive-by-wires that most of us probably use today, where you have sort of electrical signals helping you drive the car. And then electrical outlets, different ways of generating power. There are diesel generators and water wheels. Again, just implementations of some kind of abstract idea, which is in this case generating power. And I bring all this up because files are another kind of abstraction. So you can give a ton of examples of abstractions. Files are just another example of an abstraction. And what are they abstracting? What exactly is the abstraction for? Well, it's abstracting out how to read and write bytes. And really it's typically across storage hardware, but as we'll see, not really covering this course too much, but as we might see later, files don't have to correspond directly to bytes on your physical hardware. There are like pseudo files and network socket files. As long as you can read and write bytes to it, that's really all you need for it to be considered a file. So again, yeah, reading bytes of data, writing bytes of data. The saying is in Linux that everything is a file. So to sort of demonstrate this, I'm going to open up another window here on the right, zoom in, go to my desktop, make a directory, call it files, and in here, I'll just create a hello world program. And I can cat out the contents of this file using cat to view its ASCII representation, the characters in this file, I should say. But to really view the contents of this file, or the numbers behind this file, the bytes, I can use a tool called hexdump. This is just to show you that a file really is just mapping to a sequence of bytes on disk. And if I do this, you'll see this like really unintelligible output. It's just numbers, sequences of numbers. To make this a bit clearer, what we can do, now these are hexadecimal numbers, so does anyone know what hexadecimal is? Yeah, so.
Binaries at base 2, while hex is at base 16. So
Yeah.
each character in hex can represent a wide array of binary nibbles.
Yeah, exactly. So every hexadecimal digit is a value 1 through 15, right? So that's why you see values like E and A here represent those values beyond 10. And to make this a bit more manageable, we can actually pass the -C flag to hexdump. And the C stands for canonical or true. And this gives you like the canonical output of this program. Maybe what I'll do is make this full screen for a second so you can really see it. There we go. And you can see on the right here, it actually prints the characters that each byte corresponds to. Now, you might wonder, how does it actually know, how does hexdump know what character each byte corresponds to? And that's not something that hexdump really is in charge of knowing. That's something that comes from the ASCII table. So the ASCII table, I don't know if anyone has heard of this before. Yeah? Does anyone want to maybe explain it before I do?
So the ASCII table is just a standardized way of representing the most common characters using, is it 256?
Yeah, 256 numbers. So because values on disk, the values that files map to are stored as byte sequences, we need a way as humans, computers understand those bytes, so we need a way as humans to understand what is actually being stored. And so the ASCII table is a way to encode those byte sequences and map them to characters that we can understand. And if you just type in man ASCII, you can see the ASCII table. Oh, do you have a question?
Well, that was what I was asking.
Okay. So man ASCII, you can scroll down, and you can actually see there's the whole ASCII table laid out here for us. There's the octal representation, octal is base 8. The decimal representation up to 255, I believe, is what ASCII goes up to. You can see right here, 127. Maybe it's 128, I guess. I only see numbers up to 127, but interesting. So, yeah. And then hexadecimal, which is most interesting to us right now because we're looking at hexdump's output, which is in hexadecimal. So what I'm going to do is open this in the bottom. Open the ASCII table down here. And we can see the first character here is hashtag. The first byte sequence in base 16 is 23. So if we look in the hexadecimal table here in the bottom and scroll down to 23, we can see it maps to hashtag. So again, the data the file maps to on your disk, the data that is what the file is pointing to, is not actually these characters, it's these byte sequences. And we have, and tools that we use, editors, paging tools like less or more, they decode these bytes into characters for us to be able to read. Just trying to peel away the abstractions so you can see what's exactly going on. And the file is an abstraction for letting us read and write these bytes regardless of what hardware we're working with. So I'm on an Intel machine. Some of you might be on an AMD machine or other kinds of hardware. And files will still work the same way. You can read and write to the bytes of them regardless of the hardware underlying your machine. And really what's enabling us to do this is the kernel itself, and we'll talk more about that later. So what about file extensions? So again, yeah, files are oblivious to their extensions. Again, the file name is like a map. The file's contents is the territory. So if I have a map of the United States and I make Florida larger in the map and I draw Texas as smaller, I'm not actually changing the size of Florida or Texas, right? I'm just changing what the map says about them. If I tear up the map, I don't cause an earthquake. If I set California on fire, I don't cause wildfires. We have enough of those. And if I dump the map in water, I don't create a tsunami or flood or anything. The map is not the same thing as reality. Likewise, a file's name is not the same thing as the bytes the file is associated with. So file extensions don't really correspond to anything for most programs. Some programs do use them to kind of infer things for the user, but they're not actually part of the file itself. Yeah?
How does this work with like files like Java files where there are like conditions on what the file name has to be based on the contents of the file?
Like .java or .class?
Or like
Like when you create a class in Java, it actually requires that the class name is the same as the file name.
Oh, well, that's required by Java itself. So the Java compiler will be looking at the file names to match the class name. That's something where the tool you're using actually looks at the file name. And we're going to see another tool shortly in this lecture that does the same thing, where it looks at file names and their extensions to infer data about them. Yeah. So I actually don't have a MP3 file downloaded at the ready. Maybe I can find one. Let me see if I have one from the previous semester. Otherwise, I'm going to have to try and find one online, which could be kind of weird. So let's see if I can find a file here. Lecture files, file. Beep store. I had a file called beep.wav that I used a while ago, but I don't think it's here anymore.
Do you want to use find to find the MP3 extension?
Well, I just tried to find it by the. I could search by the extension, sure. But I just tried to find it by the name and I couldn't find it. That's what that find command was doing. I can just search for a beep sound effect really quick. We can download one. Yeah, I want to prove a point about what. Now, there's more than just file extensions. Files, data themselves can actually tell you what kind of file you're dealing with, and I wanted to see if I can find one here that can illustrate this concept for me. Can you hear it? It's very, very light, but that's probably for the best. Okay, so this is not what I was planning on using. I was planning on using a WAV file, but MP3 should be fine, I think. So we have our files in the desktop. Yeah, hello.c, and then I'm going to move that download, that file for my downloads, beep.mp3 here as well. And I can run this command, file, hello.c, and file is a unique command in that it doesn't actually look at the file extension. It will actually look at the file's contents and try and determine what kind of file has been passed to it. So it actually looks at the bytes of the file itself. And there's a few things file does to determine this. For C projects, I'm not entirely sure, but it checks. I mean, you can see it has ASCII text encoding. It probably inferred that based off the encoding used for the file. But for, let's see, beep.mp3, it can infer that it is an audio file with ID3 version 2.4. So ID3 is a tag system that you can add to MP3 or audio files, and it lets you store metadata about a file, a music file, like the artist's name, the album name, etc. So we can see file is able to infer that this MP3 file is an audio file with this ID3 versioning metadata system attached to it. Now, the question is, how can it actually tell this about this file? All we have is this MP3 file with a file extension. How can it actually infer any of this? And okay, we'll see that shortly. Kind of to demonstrate that file is really just looking at to drive home the point that file is really looking at the contents of the file and not just this file extension. I'm going to copy this hello.c file to an MP3 file here. And if I try and open this or run file on this hello.mp3 file, you can see it still is able to detect that it's a C source file with ASCII text. It's not actually looking at the extension at all. It looks at the contents and can tell that it's really just a C source file with ASCII text. I can do something similar with beep.mp3. I move it to beep.c. It still detects that it's an audio file with this MP3 or ID3 metadata system attached. Now, some commands do look at file extensions. So as you mentioned, Java before looks at the file name. The open command, which is really short for xtg open, they're the same thing, will actually look at a file that you pass to it and look at the extension and then use the extension to determine what program to open this file with and open it for you. So if I pass hello.mp3 to this open command, it will try and open the file using a media player, but because hello.mp3 was copied from a C file, it's really not a valid mp3 file at all. So nothing happens. Now if I were to open the beep.mp3 file here, you can hear that it works. And if I open hello.c here, it will open it in a default text editor for my system, which I guess is Visual Vim, GVim, GUI Vim. So, yeah. Yeah, so we have files of different types. I mean, text files are strings of characters, program files. We had mentioned this last time. So when we compile a .c file to .o file, what is a .o file? What is that object file? What is it? And what is it, what kind of, I mean, it says it here, it's machine code, basically. Binary code that we just can't run yet because it doesn't have it has not been linked with everything it needs to be linked with to actually run. And other kinds of files, media files, images, music, etc. Sequences a byte in a format recognized by applications. So these are just specific like standards we've agreed on for formatting music files, audio files, image files, etc., so that we can play them back with different pieces of software. And to really show you, like, okay, so now I guess to answer how it is that the file command can tell the type of this file, an audio file with ID3 version 2.4.0, I want to show something here. Hexdump-c beep.mp3. So what does hexdump do? We just saw it.
Copies each character, maps each character to hexadecimal.
So close. I'll get rid of the -c, or I'll leave the -c here. What is hexdump by itself doing?
It's outputting the binary or as hexadecimal, but the contents of the file.
Yeah, so maybe that's what you were saying, and I didn't interpret it correctly. But it prints out the contents of the file in a hexadecimal representation, and then -c will add the ASCII representation of those characters. So if we run this, we can see it's a pretty big file, not too big. And the first 3 characters are ID3. So let's go back to this window here. I'm going to click on this. And this is actually the source code for file. So all these tools we use in Linux, pretty much all of them are free open source software, FOSS, free open source software. This is by design. The people who made Linux and made like a lot of these utilities are like strong proponents of making all the software open source. And this is actually the part of the code where file checks how or what kind of file it has been passed. And it does this using what's called a magic byte sequence. So in this directory here, we have all the magic byte sequences of different files. Magic bytes are sequences of bytes at the very beginning of a file that can tell you what kind of file follows, what kind of file is stored. So in the case here, file says at position 0 in this file, there should be a string ID3. And if you see that, that means you're dealing with an ID3 file, an audio file with ID3 tag encoding. And we can see right here, at position 0, the beginning of this file, there is the string, the text, ID3, which means we're dealing with an MP3 file with, or an audio file with ID3 tag encoding. So like by tags, I mean like artist, album, those sorts of things. And that's why if we run file on beep.mp3, we can see it actually is able to detect all this. It just reads the first few bytes of the file and can see that that magic byte sequence is there that corresponds to an MP3 file with ID3 tagging, and then it can tell you based off that this is what kind of file we're working with. And if you're confused still, you can open up the man pages for file, and we'll actually tell you all the tests it does to check what kind of file you're working with. So file system tests, magic tests for magic byte sequences, and language tests. So I don't know what file system tests are. I think they are checking whether or not a file is a directory or a regular file. Magic tests are checking those magic byte sequences that we just saw. And then language tests, I presume file is doing some sort of, it somehow reads the contents of the file to determine what kind of programming language you're dealing with. That's how it could tell us if we were dealing with a C file for hello.c. Okay, so any questions before I continue? Yeah.
Do you know why it's called magic bytes?
Because it's arbitrarily selected. I think that's why. Whenever you have some kind of arbitrarily selected value in computer science, people call it magic. Which, you know, magic is bad. But in these cases, they're all encoded here, so it's okay. We've all agreed on it. Yeah?
Is the file's like size stored in the file?
No, the file size is not stored in the file. That's stored somewhere else that we will talk about later.
So if you like send the file somewhere that
is that like, I guess, is that information about its size sent like along with? the
You have to,
file?
depends on how you're sending it, you might have to specify the size of the file you're sending along with the file. And this can be a vector for attacks because you can specify an incorrect size and then send more data than you specified in the size, or yeah, more data than you said you were going to send, and then override what the tool was expecting, whatever the recipient was expecting, and then inject some code or something. This is an attack vector. Yeah. That happens when you send files over a network, for instance. Okay, where were we? Yeah, and speaking of attacks, that leads to the next point here. If a file's extension doesn't really tell you anything about a file, then you can actually trick people or trick machines into thinking that one file is one type when it's really a different kind, just by using this extension. If the tool is going to read the extension and expect one kind of file, you can kind of sneak another kind of file type in there by just making the file name not match what the file's contents actually are. And a famous example of this, so this technique is called masquerading. You can see there's a whole, it's in cataloged on one of these attack vector cataloging websites, MITRE. Over here, maybe I can, yeah, I gotta stop, I have to open this in a new tab so I don't, whatever, I can just explain this one. So, a really famous example of masquerading was the I Love You computer worm. This came out in, I think, like the 90s or something. It's pretty old. And the way this worked was that the worm, the attacker, initially sent an email to someone, and it had this message in here: kindly check the attached love letter coming from me. And I guess it was supposed to entice you into wanting to open it because it said it was a love letter. So you'd open the file, and it said loveletter.txt, but because Windows machines at the time hid this VBS extension, all users saw was just .txt. So people reading this email would see this loveletterforyou.txt file. The .vbs extension will be hidden, and .vbs is Visual Basic Script. So it's actually a program that Windows runs if you click on the file. So users were tricked into opening this file based off the file name and extension. And they would run this script, and what it would do is do what worms typically do, which is open up the user's email client and just send itself out, propagate itself to everybody in the user's email list. And what's kind of funny is that the gentleman who made this attack, he was from the Philippines, and at the time the Philippines had no laws against cybercrime, so they actually couldn't prosecute him at all. They just kind of had to give him a slap on the wrist and say, don't do it again, and that was it. And they made rules immediately after that, but
Was that all it did? It was just a prank?
yeah, it just is a computer worm. So I think it would actually, I don't know if it would copy itself on your own file system, but that's what worms typically do. They just copy themselves and spread like wildfire. And some worms do actually just copy themselves on your own machine and then take up all your disk space, and then you're kind of out of luck. So, yeah. Yeah, I don't know, what was it? The Morris worm is a classic example of another classic example of a worm, where Bob Morris, he made a worm, I think by accident actually, that really spread like a bunch across different universities. Yeah. This is another one, also pretty bad. This one actually has like more real-world ramifications, not just a worm. Basically, the attackers moved this TXT file to an exe file. I forget exactly what the goal of this was. But basically, they got people to run an exe file that shouldn't have been ran. Oops. Yeah.
Isn't there supposed to be compatibility issues sending people binaries that you compiled?
So I think the attackers actually had access to the target machine. So they actually ran this command on the target machine. Like it wasn't like you sent this file. They didn't send this file to someone else. Or were you talking about here?
No, the exe. Yeah.
Oops. Yeah, I think the attackers were actually, I haven't read the details in this attack. There's a paper associated with it. You can read here for all the details. Basically, yeah, the attackers renamed this file and then tricked people into running it. Yeah. Another example. Okay, so how do files actually get named? So we give files names based off of their path, right? Their path in a file system. So I guess quick refresher, what's an absolute path versus a relative path?
The absolute path is the path to the file with respect to the root, whereas the relative path is the path to the file with respect to wherever you're at right now.
Yeah, exactly. So relative paths are relative to the current working directory. Absolute paths start with the root, the slash, they're from the root of the file system. Let me check what else is up here before I... Okay. So under the hood, what's going on is that each directory file is mapping each file name in that directory to what's called an inode number. So an inode number is like a unique identification number for each file. And I'll actually draw this here for you. If we have a directory, or a root directory here, then there is going to be a table, essentially. You can think of what a directory is as like a table. I mean, you've all seen hash tables before, I assume. You've taken CS1 at this point, so you should be familiar with hash maps, hash tables. If you're coming from Python, like dictionaries. And what this table will store is a mapping between file names and their inode numbers. So the special directory dot, what does dot refer to?
Current.
The current directory. And then dot dot,
Parent.
the parent. And then what's the special case for the root?
Tilde.
Or what is the root, what does the parent of the root refer to?
Set.
Itself. Yeah, it's a special case. So then we'll say there's a user directory underneath the root directory. Now, I'll give these inode numbers. So dot is, we'll say 0. The root directory's ID is 0. What should the ID of dot dot be? So not 1, but if the ID, if the dot dot also points to the root directory itself, in the case of the root directory, remember, the parent of the root directory is the root itself. Its inode number should be the same as dot, which should also be 0. And then user we can say is 1. We'll just assume user is 1. So we'll just draw some quick arrows here. Maybe I should draw that in a different color so it's clear what the distinction is. Okay, now the root directory has its own mapping from names to their inodes, and the user directory, if we have files in there, it will have its own mapping as well. So I'm going to copy this, copy what we have so far, and I'll create it again for the user directory. And I'll copy this, drag it down. I can just delete that slash here. Oops, not what I want to delete. There we go. And we'll say user bin is the next directory down. Okay, so we'll assume that bin has a inode number of 3, or 2 I should say, if we're going to go up sequentially. What would the inode number of the dot directory be here? 1, right? Why is it 1? It's itself, and we already know in the parents directory that it should be 1. What about dot dot? What should that be?
0.
0, right? Because we're going up the directory tree to the root, and we already know the root's inode number is 0. Now you can actually check this on your machine. I can go to my root file here, my root here. I think it's the -I flag to view the inode number. ID, there we go. So root has an inode number of 2. If I ls-d, so what -d does, and we're using the -d flag here, ls prints my current directory's contents. -I will print their inode numbers as well. And what -d does is it tells me to print a directory as a file, not to print its contents. So if I were to say ls/ like this, normally it would print the contents of the root directory, but with the -d flag, I print just the root directory itself as a file. That's all I do. So by combining these two flags, di, I can print the root directory and its inode number. Does that make sense? Does anyone have any questions about all those flags being combined? Yeah.
I also tried doing ls-ia.
Okay.
That worked for me too.
That'll print everything.
Yeah.
So A is all. I'm only concerned with the root directory here. That's why I'm specifying di. Yeah.
Sorry, I just noticed when you did that AI one, there are a couple that have the same IO number.
Yes, that's what I'm going to get to next. So I'm glad you saw that. Very perspective. Okay. So di for / is here. If I go into the user directory and I say ls-di dot, what do we expect the inode number to be? And you can see it's in fact 2 because the parent of the user directory is the root, which is you saw is 2. And so now let's do this another way. If I go back into the root and I ls-di the user directory, I can see its inode number is this long number here. And now if I go into the root directory, or the user directory, ls-di dot, it is in fact the same as it was when I was in the root directory. So your operating system creates inode numbers for you, or assigns them for you, I should say. When you first create your operating system, when you first initialize it, it will assign you a finite number of inodes. And when you reach that limit, you can actually create more files. It's a pretty high number. There's a way to check it. I forget which command you have to run to check it. I can Google it right now. Ubuntu check inode numbers. Which command was it? df? Yeah, df, that's it. -i. You can see how many inodes I have in my file system. So my root file system right here, root, mounted on root, 29% of all my inodes are being used. So how inodes are created, how they're assigned, that's not really a topic for this course. If you want to know more about this, I recommend reading this book, OSTEP. I recommended it to one student last time, I think. This is like a free online book for operating systems. It's pretty well written. It's written by a married couple, and they have a pretty good tone. It's actually like fun to read. They're kind of witty, kind of funny. They have notes at the end of each chapter where they recommend different things to check out. So if you want to read more about operating systems, because we don't require operating system as a course anymore at UCF, I'd recommend reading this book. Or you can take OS here at UCF. Because we no longer teach OS, in order to receive that accreditation, so that's like the accreditors are what give the university the authority to bestow degrees on people. The accreditor for UCF actually requires that we teach operating system concepts. So even though we don't have an OS course, the concepts that are taught in it are now spread out amongst all the different OS classes. So you kind of get not as concentrated of information with OS, unfortunately. Okay, let me see. What's next here? Yeah, and the inode numbers. Getting is easy. Okay, yeah. Before we continue, I think now is a good point to take a break and take attendance. Okay, so I'll close this. Yeah. So guess these previous slides here. Why should we separate the name from a file? What are some advantages of doing that? I guess to illustrate this concept, if we associate each file with its inode number by using this sort of mapping schema, then how can I implement renaming a file? How could I rename user to, I don't know, user? How would I achieve this in this mapping here?
Assuming you didn't necessarily have a pointer directly linked to every single file, you would have to pop the file and then re-add a duplicate of it with the
Well, speak conceptually. Conceptually, what do I have to do to this table? Yeah?
All you have to do is change the actual name. You don't have to change the house.
Yeah, I can just change the name of the table with what value it's associated with. So because inode numbers, well, not because inode numbers, but essentially we just change the key. If you can think of it as a key value mapping, you can just change the key in this hash map, and then that's it. You don't have to actually do any moving of bytes. So if we were to store the file's name in the file's contents themselves, in order to do a rename, we would actually have to move or copy all the bytes in that file to a different location. And that would be like a total waste of resources. So it's much more efficient to just disassociate a file's name from its contents. How would I do a move? So let's say I wanted to move the bin directory here. I'll just grab this up here and delete these. If I wanted to move the bin directory up here, how would I do that? How would I achieve that goal? Yeah?
You add another mapping or cell.
Okay, so that's one thing I would do. What else would I have to do?
Can you change it to 1?
Change the bin graph to have dot dot equal.
Yeah, just remove the, I'd have to delete bin from the directory, the user directory,
Yeah.
that mapping. So, yeah,
Is it different from user?
is what?
Is it different from when you renamed it to?
Oh yeah, this should still be user, you're right. That's just for the graph purposes, the diagram, but yeah, you're right. So maybe you can see the benefit, hopefully, of having this disassociation between the name and the inode, and the contents of the file, is that we can quickly move files around by just moving their, by swapping out and manipulating entries in this key value mapping that directories are. Yeah?
Does every directory have a table, or is there like one big like table at the top level?
So each directory is a table, but there is like there are internal tables mapping inode numbers to like more about a file, which you can actually view. I'm glad you asked this because that's something I should have mentioned earlier. In the man pages, you can view information about inodes and what each inode tells you about a file. So it tells you it has metadata about the file. You can actually retrieve this metadata using stat. So that's a command we're going to see later that you'll actually be using quite a bit. I can run stat on this hello.c file, and it will tell me what the name of the file is, its size. The inode number stores that as well. So I think someone had asked that before, where we can get the size of the file. The number of blocks it takes up, that's another term that I'm not too well versed in. I'm not well versed in architecture. The kind of file it is, a regular file. The access privileges. So I won't get too into this yet, but basically files can have read, write, and execute privileges. And they can be divided or changed based on the user, the group, and others. This just specifies that we have read, write privileges as the user, the owner of this file. And then what's also useful here are these access times, these timestamps. You can see when the file was last accessed, when it was last modified, when its metadata was last changed. I know these are kind of confusing. Modify and change sound like synonyms. Change is like when metadata of a file has been changed, when any of this stat information has been altered. And then when the file was created, its birth time. I've actually been using the stats syscall for some research work that I've been doing lately. So, and actually, this is what helped me get to Brazil last semester when I went on a research trip to Rio. I used the stats syscall to help me achieve that. So, this stuff is actually very useful in the real world. Yeah.
What would you normally use the stat command call aside from like regular research and stuff?
If you wanted to check, again, access times, like if you were a sysadmin and you wanted to check when a file was last used, maybe you suspect somebody's been doing something nefarious on your server, you would check the access times, that could be one use case. And yeah, checking the permissions in a file to see whether or not it has the expected permissions. If you can't execute a file and you want to know why, you can run stat on it to see what the permissions are. You might just not have the permissions to execute the file. There are other reasons that are a bit more specific that I won't get into yet, that you might see in the very last day of class. So, yeah.
If the file didn't originate from your computer, would the birth time reflect that?
So that depends on how it was sent to you. There are certain commands you can use to send files without altering their timestamps, and then the birth time would stay the same. But if you were just copying it off some other server without any of those flags, it would change. Yeah, you can also change it. Yeah, I'm not sure what the default is, but you can change. It depends on how you do that. Yeah.
Is there a way to like change this information?
Yes, there is. You can change this information without actually modifying the file. You can kind of tamper with these timestamps. And there's actually a name for that in the security realm. It's called time stomping when you're modifying the timestamps like that. So. Okay, hopefully that was a good answer. I went on a bit of a tangent, but that was actually very, very useful, I think. Okay, let's see. Yeah, so directories are also files. Maybe you've inferred this by now, but a directory is really just a file. The only difference is that it's a directory file. So if I run stat on here, you can see that the file type, whereas before on a hello.c we saw that it was a regular file, the type here is a directory file. And again, you can view all the information about this on the man pages for inodes. It tells you more about what inodes provide. And something else I want to mention that I forgot to mention until now, but I think it's important, is that if you run man on man, you can see that the manual pages are divided into sections. We're going to see more about this later when we get into system calls in the next sequence of lectures, the next set of lectures. But we saw that the inode was on man page 7. 7 corresponds to miscellaneous information. So you can always check what inode number you're on, or man page section you're in, with the number at the top. So man 7, or man inode, you can see we're in manual page section 7 for inode information. This is useful because you might want to disambiguate it. There are different things in the man pages that have the same name. You can distinguish them from each other by using that section number. And we'll see more of that later when we get to syscalls, but I just want to mention it now. We'll see it in more detail in the next lecture. So we saw this, we demoed all this, moving a file, renaming a file. Now I want to talk about links. This is something that was not really covered in the previous course, or when Dr. Gazzillo taught the course, but I think it's useful to know this. Let me remove the beep.c file and the hello.mp3 file here. Okay. I'm going to create some more of this diagram here. Let me copy some of the content that we have. So I'm going to make a table here for my desktop. Files. And we have, I'll delete the root and parent entries here just for more space. we have hello.c, and we have beep.mp3. Let's take it a bit wider. Let's get the real inode numbers for these files. So how do we get the inode numbers of a file? What's one way to check it? What? Stat. Stat works. So we can say hello.c, and it tells us the inode number right here. So I'll copy that for hello.c, put it into this diagram. I'll open this on the left here. Get a bit smaller. Really, we don't actually need the drawing. I'll just focus on the table. Sorry, sometimes my terminal freezes when I put it to the side. There we go. Now I can type. So stat beep.mp3, we can see we have right here this inode number. So I'll put that in here. And I'll just delete these entries. We're not concerned with the special directories right now. So we can actually take advantage of the fact that directories are just mappings between names and inode numbers to implement different kinds of what are called links. So links are like ways to provide shortcuts to different kinds of files. And one kind of link would be, the first kind of link is a hard link. And you can create links using the ln command, ln for link. So I can say ln beep hard link, bless you, .c or .mp3. And then I can specify the name of what I want to link to. I got the order mixed up. It's the destination, or source first, and then the destination. Now if I look, there's a file here, beep_hardlink.mp3. Maybe I'll just rename this to HL for more space. And if I run stat on, I'll move this, rename this file to make its name shorter. If I run stat on this file, we can see the inode number is actually the same. So what is, conceptually, what is a hard link doing? It's another pointer, right? It's just another entry in this table. The value that it maps to is still the same. And it works because what's one restriction on hash maps about the keys? What do the keys in a hash map all have to be? Unique, different, yeah. So as long as they're different, we can actually do this. We can have multiple links point to the same file. And what's cool, just to really drive home the point that a file's name is not associated with its contents, I can actually remove the original beep file here, beep.mp3, and if I open beep.hl, it still works. This is just to reinforce the idea that the file's name is not the same as the file itself. The hard link is just another entry point to that file's contents. So if you want another way to look at it, I'm going to attempt to draw a house here. So we can say this house has the number, this number associated with it. Send this to the front. Can I? There we go. So one analogy to use for understanding links is that each link is sort of like a new door to your house. For hard links. Each hard link is like a new door for your house. Make this a bit wider. It's a pretty wide house, I guess. And we have beep.hl as well. And each one of these links is not the same thing as the house itself. I can add more of these hard links to create more doors on this house. And if I delete one of these doors, so if I delete, I deleted beep.mp3, I can delete that, the house is still there. The contents still remain. Now, the other thing we can do, which is different from hard links, is to create soft links. So I can create a soft link by passing the -s flag to ln. So now I can say ln beep sl, soft link, symbolic link, beep hl, oops, I'll put .mp3 here. Oh wait, I got the order mixed up again. I always get the order mixed up. And if I look at the inode number for beep SL, what do we think it's going to be? The same as is it going to be the same as this number here, or a different number? So this is a soft link. So to illustrate the point, I guess, it's actually a different inode number. So soft links to files are completely different files, completely different inode numbers. When you open them, you're essentially redirected immediately to the file that they're linking to. So continuing with this very crude illustration, beep SL, the soft link, is essentially a sort of tunnel to the house, is what you can think of it as. I don't really know how to draw a tunnel, but maybe like a path or something. I don't know.
What's the benefit of having it?
The benefit, well, I mean, it depends on the scenario in which you're using it. One benefit is that you don't have different files. So if you're modifying, well,
Is it like a shortcut?
it is a shortcut essentially. It's a shortcut. Now the benefit over a hard link, I can't tell you off the top of my head a scenario in which you'd want to use a soft link over a hard link. One thing that's cool about soft links is that they're relative. The links the destinations are relative. You can have a relative directory as the destination, so you can actually copy those soft links around in programs with other people. You can pass them to other people, and the soft links will still work as long as the relative paths they refer to are the same. So you could use it as a shortcut for that purpose. I use soft links for configuration files when I'm making links to configuration files on my own machine. I can show you that later, like in office hours. But that's not really. I don't need to use soft links for that. I could use hard links just as well. So yeah. So if I were to, in this case, with soft links, and maybe here's one reason why you want to have a soft link. If I were to delete beep HL, what do you think is going to happen to beep SL? Will it still work? No, right? So if I remove beep.hl and then try and open beep SL, it says it can't open it. Failed to find default application content type for inode symlink. It can't even open what the symlink refers to. And if I do ls here, you can see my terminal actually highlights it in this red dangerous color to show that it no longer is. It's a dead link is what we call it. You can actually run stat on a soft link and see what it points to. I think there's flags you can pass to ls. I don't know what all these stand for, but I've used them before, and you can see that here. It also shows you what they point to. I think maybe it's the -r flag. Maybe -h. Yeah, -l will show you what the soft links point to. So this is akin to, again, in this analogy, deleting the house but leaving the tunnel. The tunnel leads nowhere now. Now, on the other hand, if we were to have just deleted the soft link, the house would be unaffected because the tunnel is not the house. So you'll see soft links and hard links crop up as you're working on other machines. So I think it's important to know the distinction, what they are actually. Yeah.
Did you do a soft link to another soft link?
You could, yeah. I don't think you can soft link. You can have a link point to itself though. There are no circular links allowed. Yeah.
The tunnel collapsed because that hard link was removed. If we had two hard links into the same inode and then one of them was removed, would it matter which one had been used to establish the soft link?
It would matter because the soft link is linking to the name of the file.
Okay.
So if the one that the link was made to link to was deleted, then it wouldn't work anymore.
Okay.
Yeah, yeah.
Do you have the problem where if you were to delete the hard link, like if you were to delete the feed hard link, would the file still exist? You just could get to it?
So that's a good point. The file would, the bytes would still be there in your machine, but there's no longer any inode associated with those bytes. So now other files, other programs are free to override those bytes as they need to. So they're not really, the RM command, for instance, doesn't really delete a file immediately. It doesn't zero out the bytes. It just frees up those bytes for other programs to overwrite as they want to after that. Which is effectively the same thing as deleting it, because there's no longer any way to just access those bytes on your machine. You've lost the way to access them. That's why another synonym for deleting a file, and you'll see this as another synonym on like a more lower level way of deleting files, the command is called unlink, because you remove all the links to the file. Yeah?
Does it have to be a file or could it also be a directory?
For linking to? Yeah, you can link to a directory. You can also link to a directory. Okay, so let's see where we are in the slides. Yeah, okay. So I think we've seen this already. Directories can contain other directories. We've seen this. We've been diagramming this, showing this. The root directory can contain the user directory, can contain the include directory or the bin directory, etc. And what happens when we do this, we have all these directories containing other directories. What do we have as a result? What kind of structure do we form? A tree structure. We get the hierarchical file system, as it's called. And this is pretty cool because this is something that people had to actually invent themselves. There's actually a paper. I think we have it here. No, somewhere in the website here. File basics. Yeah. Maybe this is it? No. Well, I think I know where it is. It's right in the recommended reading. Yeah, right here. This actually explains the Unix system and the file system a lot in this paper. It's a pretty readable paper. It's from, let's see when it was published. In 1974. So it's an old paper, but honestly pretty easy to read, especially if you're not like someone who's into like computer science literature. You can actually read this paper pretty easily. And it explains how like the Unix file system works, which was pretty innovative back in the day. We kind of take this hierarchical file system for granted now, but it wasn't something that people had to think of this up. It wasn't something that just was naturally obvious that we should organize files this way. Because there are other file systems out there that are not hierarchical. I don't know if anyone has ever used tags to organize music or other kinds of media before. That is another form of file system. There are file systems that are tag-based. They don't use directory structures at all. It's just all tags. And there are pros and cons to each approach. So we've already seen all this. Does anyone want any review? I think we are probably pretty familiar with all the stuff on this slide. The root directory, separating directories, the dot, yeah, paths, absolute paths, relative paths, working directory, parent directory. We've seen all this. Okay, so you can do other things with files besides map to read and write byte sequences that are stored on your disk. You can have what are called pseudo files on Linux, or you can have like network sockets. So actually I can go to my, let's see here, CD, my root directory. There is a, let's see, there's directory somewhere in here. I think it's slash sys slash, where is it? I cannot remember where the network directory is right now, but basically every network access, network sockets, ways of transferring bytes across the network are mapped to actual files in your machine as well, and you can write and read from those files directly to write and read to across a network connection. I forget exactly where they are. Maybe they're in my user directory, my UC directory. Well, I think it's in the dev directory actually. Yeah, dev, net. Yeah, and these are all like, I think this is where like the network sockets would go if I had connections open. There's also the proc directory. So every single running program on my machine, on your machines if you're running Linux, every running program has an entry in this proc directory. Every process has an ID, kind of similar. Every running program has an ID, similar to how files have inode numbers. And information about these running programs are all stored in this proc directory. And we'll see more about running programs and processes later. Oops. One really important sudo file descriptor that we have access to is /dev null. So dev null is like the empty file descriptor or file. So we can read and write from this and nothing will happen. So I can echo, well, if I were to echo out some text, so hello world, what all echo does is print out what you pass to it. So I can say hello world and print hello world to the screen. I think we saw earlier we can use this redirect operator to redirect the output to a file. I think maybe we saw that before. So briefly, we'll go over this in more detail later, but briefly, the redirect operator redirects output to a specific file. If you redirect something to dev null, it just disappears. It goes away. It's pretty useful to do this, to just throw out the output of a command that you don't want the output of. So you'll often see scripts and things, even in this course, we'd use this in the grading scripts. We just redirect output to dev null to throw away some output. Like if I did ls and then redirected this to dev null, nothing would happen. So you can write to dev mem to write directly to RAM. You probably don't want to do this unless you know what you're doing. Kernel settings information in proc. Graphics, you can write directly to your graphics. Peripherals. Actually, what's cool is if I go into the media directory, any flash drives I have attached are going to be in my media directory here. I don't have any media right now, nothing's attached. But this is dissimilar from Windows, in which if you plug in a USB, what happens? Is it going to be underneath your C drive, or no? Right? You get a new drive for that USB stick. It's a whole new drive. It could be like E, Z, whatever. In Linux, it would actually be in this media directory. So it's all underneath the root. Everything is underneath the one file system. Yeah, so I mean the idea is, yeah, again, files are abstractions. You can use them to read and write bytes to and from disk, but not just disk, also across the network to these special file descriptors like dev null. I think actually there's one more that's kind of cool, which is dev random. What do you think this is going to do? Just prints out random garbage. So what you could do is use the head command to print out just the first 10 lines of output. And I could pass dev random to this and just get some random numbers, some random input, random bytes for some purpose if I wanted random numbers for some reason. Okay, and that wraps up today's lecture. So we're a little early, that's fine. If you have questions, you can ask me, or you can come to me during office hours. Remember, next Monday there is no class. I think we have the day off, right? It's a holiday. So, yep, no class. And then on next Wednesday we'll go over syscalls. That'll be pretty fun. So, yeah. Yeah, you can look stuff up. Yeah.
Oh, okay. I didn't know.
But you can look in the course notes too. The course notes should hopefully be able to answer your questions, but if not, then you can just Google stuff.
Also, I'm gonna go to office hours tomorrow, but just as a general thing, the recommended reading, is that lecture per period, for deeper understanding?
Yeah, you really don't need the recommended reading, but it would help. You don't need to do it strictly. But it would help you, especially when you do the projects later on. it will greatly enhance your understanding of the material if you do the reading.
Okay.
It's better than going online, because online is like all, you can get direct answers to questions, but it's all scattershot, whereas a textbook is like a cohesive narrative where someone has like intentionally thought about what kind of questions you might have reading this material, and they'll answer it for you as you're reading.
Yeah. Okay. Thank
Yep,
you.
You're welcome. Have a good one.
You too.
Sorry, is there any way to keep track of the links you've set up? Like, or is that just like memory? Just to know that you've set up before, if you want to.
Like hard links and soft links, you mean?
Yeah.
You would just have to run ls in your directory and look at what files are links. Or,
Oh.
yeah, you can just run stat in a file and it'll tell you what kind of file it is. So, well, let me actually save the recording here.